Welcome back to the second day of our 3-day event, MSENSE Digital Event. We're broadcasting live from the MR headquarters in Regensburg in Germany. On our second day, we even turn up the pace for you. We have more interesting presentations, more thrilling FAQ rounds, and our chat team is waiting for you all the time to bring in your good questions. And we prepared all of this especially for you, our valued customers. So please enjoy the show today. For our first presentation, we invited two guests, Laurenc Kirchner and Tobias Gruber. Tobias is part of the MR family for over 8 years now, and he is the portfolio manager for Ethos. Laurenc is working for MR for more than 10 years, and before that, he was working at Mikafil, the bushing manufacturer, as the manager of the test field there for over 10 years. Together, they will tell you about the ways of detecting errors in high voltage bushings early. So please welcome Laurenc and Tobias. Come on in.
Thank you, Peter.
Thank you. Morning. Peter, thank you for the introduction. Very warm welcome to our audience out there in digital space. Today I am going to talk about bushing basics, and Tobias later on will tell you something about our bushing monitoring system, MSENSE BM. I'm going to start from the scratch. What is a bushing? As we can see, very simple and I think clear to everyone, bushing consists of a conductor made out of copper or aluminum, surrounded by an insulation system to overcome a certain barrier that usually is connected to ground potential, and the conductor itself usually has high voltage potential and is carrying a certain current. The barriers that the insulation system usually is overcoming might be a transformer tank, the roof of a locomotive, a wall of a building, or switchgear housing. What is very important for us today is to mention that we are focusing on AC bushings. Now we would distinguish different bushing types. We have a not graded insulation bushing. That's a very simple bushing. Here we see the picture of a DIN bushing. That's a very simple device. We have ceramic shades on the air side. We have ceramic part at the oil side and the copper conductor and a bunch of sealings. That's usually used for smaller voltages, and what we see here is a cross-section of such a bushing. It's not exactly the same as we see here because the flange is a bit different, but we see here the conductor at high voltage potential and the flange is on ground potential, and what you see between here are lines that all have the same voltage level, and what you can see is that you get the high dielectric stress here and here on that point, and if you move further up the dielectric stress is much less, so you get an insulation system with a non-uniform utilization of the material. That's not optimal, but it's a cheap solution for smaller voltages. What we see here on the right side is a bushing that has one electrode to create the electric field. This, what we see here in the middle is the conductor, and it's surrounded by an insulation with silicon shades usually, and in between it's filled with SF6 gas. And what we see down there is an electrode. With this electrode you can steer the field a bit, and on the top edge of the electrode there is a certain shape, and we see that in the picture here on the right side. A simulation of the field in this area, and what we do basically is we move the dielectric stress from that point further up to that point, and we get a little bit better utilization of the electrical field and the materials, but it's still not optimal. And yeah, there are better solutions out there. We will see on the next slide, but what is very important here to mention is that this bushing and that bushing has no connection where we can connect a measurement system, so we cannot monitor these bushings. For an SF6 bushing, as we see it here, the only thing you can monitor is the pressure of the SF6 gas to detect if you get a leak or not, but you would not connect a classical bushing monitoring to that kind of bushing. We are focusing for so-called condenser bushings, and here we see such a design. We have here the flange, and it's an oil-air bushing, so this is the oil side, this is the air side. We have an insulator, silicone or porcelain, and we have a condenser core here in the middle surrounding the conductor. And there is a space between the condenser and the insulator, and usually this is filled, depending on the technology, either with oil or with some foam. I will explain that later on. And here we see a sketch of half of the part of the condenser core. The condenser core consists of many foils, basically surrounding the conductor, and with these foils I try to grade the field and get a better utilization of the insulation material. Now, what is important to know, if we look at the foils, they usually capacitances that are connected in series. If I look from the conductor to the flange, and we start here with the first foil going down to the last foil here, the ground foil, and this capacitance of all foils together is called C1. That's the main capacitance of a bushing, and we have a second capacitance called C2. You see that here in the picture, and C2 is the capacitance between the last foil, the grounded foil, and the flange. And here, number 4 is a measurement tab. This is very typical, and all condenser bushings have a measurement tab, so you can monitor them or you can do diagnosis on them. And if we look at North America, at the IEEE, we have, besides the measurement tab, also a so-called voltage tab that's described here. And what do we see here? We have the flange, and there's the ground foil, and the last foil before the ground foil is connected as a measurement or voltage tab. And that's the difference. So the insulation system here is designed for higher voltages. Usually this, or according to the standard, you have to test this voltage tab with 20 kV AC for 1 minute. This measurement tab is only tested with 2 kV for 1 minute AC. So you see the difference here in the voltage. And as I mentioned, this is usually seen in North America, this design. What is important to say, if you grade the field here, you have the highest dielectric stress on the bushing here in the oil part, usually, where you have the foils in very narrow steps to each other, and this is the most critical part of the bushing. So now, having seen that there are different types of bushings out there, before you do a monitoring, it makes sense to think about different technologies, because that might have an impact on your monitoring system. And the most well-known bushing is the oil-impregnated bushing, in German called Weichpapierdurchführung, and it's from the price side, it's very interesting bushing. It's an old proven technology, and you have oil with paper insulation, and usually the bushing manufacturer uses here the same materials as a transformer manufacturer would use in his transformer. So you have same material, the stuff is well known, the behavior, and the oil is the main insulation, and the paper is used to keep the condenser foils in place. Another technology that is, to my knowledge, not produced anymore is the so-called resin-bonded paper bushing, in German HIGH-Papierdurchführung. This is a dry epoxy resin insulation, so you get the dry bushing, and the epoxy resin was directly coated on flat paper and cured and winded on a machine. So for the manufacturer, it was an easy process, but the quality of these bushings are not so good in many cases. And I think that is maybe one of the reasons why it's not produced anymore. My personal recommendation at this point is if you have such a bushing in service, it must be at least 30 years old or older, and I would recommend to replace it. And it is difficult to monitor this bushing, and I will explain you later on why it's so difficult to monitor this bushing. A new technology is the RIP bushing, the resin impregnated bushing. That's a complete dry bushing. You have dry epoxy resin insulation that's poured and cured under vacuum. And they use usually crepe paper to keep the condenser foils in position. And even more modern is RIS and RIF. So instead of crepe paper in these technologies, they use fabric or synthetics. And it's a complete paper-free bushing, but be careful, that doesn't necessarily mean that this bushing is not sensitive to moisture. If you have a RIP or RIS bushing and you store such a bushing, it's very important to keep the oil part or the gas part, if you use it for SF6, under dry conditions. So usually you have a tank and you put this bushing or this part of the bushing in oil, in dry oil or in dry gas if you store it for a long time. If we talk about oil impregnated bushings, there's to mention that you usually cannot put them flat to ground because you have a condenser core and you have oil, and if the condenser core is exposed to air, and that usually happens if you lay it flat down to the ground, you get air inside the condenser core, and that would lead to partial discharge if you put it on the transformer, and that can destroy your bushing. So therefore, a manufacturer usually would tell you to transport this bushing at least under 15 degrees. And that's a downside of this technology. If you're looking for dry type bushings, they are much more robust. You can insert them in a transformer even in a horizontal way. You can transport them without worrying about the position of the bushing, so that would benefit on that side. And a dry type bushing usually cannot get a leak. So there can no oil run out and destroy the bushing this way. If we look at these pictures here on the next slide, we see on the left side an active part of a condenser bushing, of a OEP bushing, and we see the flat paper, it's oil impregnated, and underneath there are the conductive layers we don't see here, of course. And here we see resin bonded paper bushing, and this resin bonded paper bushing has dark areas, and these dark areas basically mean that the bushing was sucking up oil, and it's not supposed to be that way, but if they sitting in a transformer for a long time, that can happen. And if the oil goes into the bushing, the epsilon R value is changing of the bushing, and with the epsilon R value also the capacitance value is changing. And if the capacitance value is changing, that would be an indication that you lost a foil in your condenser core, but in this case you don't know it if you lost the condenser core or if oil was going into the bushing. And for that reason, it basically doesn't give you the possibility to judge the result you're measuring on this bushing. And due to the fact that they are older than 30 years, I would recommend to replace them with a new technology. Here we see a RIP bushing, and we see a void here between two layers. And due to carbonization of this void, you get the connection of these two layers. So you lost one layer, and with a bushing monitoring system, you would detect such a failure. And additionally, you can see a crack here in the bushing, and of course, it's not supposed to be that way. And before you install a bushing monitoring system, you might think about checking your bushing, especially if it's not brand new equipment. If you have older bushings on your transformer, you would like to know if they're still in good shape before you apply the bushing monitoring system. And for doing that, you might do a diagnosis on your bushings on the transformer. And if you do a diagnosis, it's very important to know the history of the bushing, because if you have to judge tongue and stealth and capacitance values, it makes a difference to know the history. We see here another example of a rip bushing that was exposed to very fast transients. That can happen if a rip bushing is connected to GIS equipment and you have operations of a disconnect and GIS. You get sparks in SF6 gas that can lead to very fast transients, and that would disturb parts of the bushing. You see here an arcing spot, and here you lost at least 4 or 5 layers of the bushing, and with a monitoring system, of course, you can detect that. If we look at this problem in a wider perspective, there was a Seeger study done in the past, not on all transformers of the world, of course, but it's an indication, and 17% of all failures are caused from bushings. And if we look closer to that, we see that 40% of these failures would lead to severe failures that end up with an explosion or with a burning transformer. And the bushing itself is not very expensive device on your transformer, but it can cause very high costs. And for that reason, it might be recommended to invest in a bushing monitoring system. And Toby would tell you more details about our MSENSE BM. Toby,
Yes.
your turn.
Thank you, Laurenc. And I'm sure also the viewers and myself learned a little bit more about bushings now. And so as we are now familiar with how bushings are looking from the inside and which technologies are there, I'd like to discuss with you how can you monitor such bushings. So once again, the major sentences that Laurenc was telling, that about 17% of the major transformer failures can be traced down to bushings. And the bushing isolation breakdown is the major reason for severe transformer failures such as fires and explosions. So there is no protection involved. So once a bushing is failing severely, also the transformer will fail. And also the typical manufacturer-specific lifetime will be about 25 to 30 years. So it's recommended when the transformer life is 40 to 60 years to replace also the bushings during the lifetime of a power transformer. And also, once again, to mention it because it's really important, the failures occur suddenly. So it's not that the failures will be there for many years and suddenly a severe breakdown will happen. So this, of course, can always be an option, but typically the failures occur suddenly, so suddenly a breakdown will happen. How can a breakdown happen? So you will face overvoltages, you will have changing operating temperatures, especially also with the feed-in of more and more renewable energies. You can have in the at the component manufacturer side already material or workmanship defects. There can be moisture intrusion or always, of course, the natural aging, and this can lead to the insulation breakdown. So if you compare it, if you apply online monitoring to conventional offline diagnosis. So online monitoring is a permanent way to assess the condition of the bushings. That means you will get a warning before the minimum condition of this bushing is reached, and it's an early fault detection. The conventional way of assessing the condition of a bushing is by offline diagnosis. That means you need to shut down the transformer and perform electrical measurements, such as the capacitance measurement or the tangent delta measurement. And you do this at defined times. For example, every 7 years, every 10 years. And then you get the condition at this defined point. But you also need to know the history of the bushing. So you need to know the values, let's say like a fingerprint from the start of the bushing's life to the very end of the bushing's life. So the failures can actually occur, but not detected with the offline diagnosis. So this does not mean that you can that you can just do online monitoring or diagnostic. It's a mixture of both, and this is a slide how you can implement online monitoring into your asset management processes. So that means if you apply online monitoring on a critical transformer on bushings, and the online monitoring has an event and tells you something happened in the change of the capacitance or in the change of the dissipation factor, then you apply a diagnosis measurement and see what is really the case. Is there maybe a hotspot in the bushing? Do I have a loss of a layer or even more layers than just one? And then you start further action. So once again, it's important to know that a monitoring system is not a protection device, but it will show warnings and alarms when something is unnormal. So how does the measuring system look like? If you look on the left side of the slide, you will see again the bushing, or how a condenser bushing will look like. You will have the C1, the main capacitance of the bushing, and then on the test tab, directly on the test tab, you can screw in a bushing adapter. The bushing adapter then contacts the last foil, and you will have a coupling unit with the perfect chosen measuring capacity, and there you then have a capacitance divider. That means from C1 to Cm, so from the main capacitance to the measuring capacitance, and then you measure a voltage that is between 60 and 100 volts, so something that you can measure and also monitor. You can see the real devices in the photos on the bottom of the slide. So you'll have a bushing. They all have different kind of test tabs, so you need to know the manufacturer of the bushing and also the voltage of the bushing. Then we choose the right measuring capacitance, and we have, for example, ETOS, where you can have the application of bushing monitoring. We call it also MSENSE BM. So MSENSE is our name for the digital or intelligent sensors, and then we will have access to the voltage of the bushings. And if we not only have access to the voltage of the bushings, but also to the reference system, we can combine these two data sources to apply bushing monitoring. So here you can see on the same side where we measure the voltages of the bushings, we also measure the voltages of the reference system by the VTs in the system. And now the question arises, why do we do that? We do that because there are two major influences if you want to apply bushing monitoring. So every bushing monitoring manufacturer has to deal with these two influences. The first one, you can see it here, is the temperature. So both critical values that you need to monitor on bushing, either the capacitance or the dissipation factor, they change quite severely with the change of the temperature. So that means that when you have different operating temperatures, you need to make sure that you always apply the right algorithms to assess the condition of the bushing and not have the temperature influences, so that you might get false alarms. And the other major parameter that you have to take into account are the network imbalances. So there are network imbalances allowed in the network, but they will directly also, if you not have the reference voltages as a source, they will directly interfere also with the bushing monitoring, as the change in the amplitude will also have a direct change in the capacitance. And the change in the angle will have direct contribution to the change of the dissipation factor to the tangent delta of the bushing. So these two major influences we have on the bushings and applying bushing monitoring. So what is now our approach at MR? At MR we use a method called double reference method. That means we assume that the three bushings, so it's always a three-phase system, and the three bushings are always having the same temperature. So it doesn't really matter if we have the temperature at 20 degrees Celsius, 80 degrees Celsius, or even minus 10 degrees Celsius, because all three bushings have the same temperature and should therefore have the same capacitance, the same dissipation factor. And not only this, so this is the temperature compensation. We also then compare the voltages that we measure from this three-phase system to the three-phase system from the VTs. And then we know is the change in the amplitude or the change in the angle, so the change in the capacitance or the change in the dissipation factor, are they really because something in the bushing changed, or is it because something in the network changed? So to have a really accurate way to do bushing monitoring, you need to compare the three bushings, but also compare the three bushings to the system reference voltage. So this approach, we call it double reference method. And if you compare this method to other methods that you can see in the field, you will see that there are advantages and disadvantages of the different approaches how to do bushing monitoring. So our major disadvantage is that we can only apply bushing monitoring on three-phase system. The major advantage, however, is that that it can be applied to almost all three-phase transformers, and it's a very accurate way also compared to other approaches to do bushing monitoring, because we don't need a temperature sensor, or we also don't need a complex way how to compensate temperature deviations or network asymmetry deviations. So the only disadvantage, again, three-phase system. Just on three-phase system it will work, but the major advantage is it works on almost every transformer, and it's a very robust way to monitor the transformer. And we can also show this out of various field tests, and since these field tests we have many applications over the world now. But just to show you a showcase, this was one of our first installations, 2014, 123 kV RIP bushings on an existing transformer, so it's possible to retrofit the system. And you can see this was a typical 10 days period, how the capacitance changes. And you can see, so we have the limit values to 5%. That means a loss of 2 layers in this case. And you can see that there is nothing happening really. This is actually what we want to see. But if one of the three phases would increase in the capacitance suddenly, we would know, okay, most certainly a foil has failed, a capacitive layer has failed, and we need to take further investigation now. The same thing you can see here also for the tangent delta monitoring. Our limit value here is 0.5%. You can see that actually nothing is happening, which is exactly what we want to see. Nothing special on a very low loaded transformer in a rural area. But you can say, yeah, this is nothing special. Every system would look like this, and I would agree. But this is also why we tested our system also in more harsh conditions, like this field test in a power plant, 420 kV. This is actually a transformer bank, but it's a three-phase system. So we applied bushing monitoring to it, and this is how the change of the capacitance looks like. So also here with a limit value of 5%, you can see we are not even close over a typical period of 10 days. And we can see that the system and the algorithm works in the field. And also we compared this approach to other approaches that are out there in the field, and no false alarms have been generated. So bushing monitoring is part of our ETOS family, part of our ETOS applications. We call it MSENSE BM. And this is one way to monitor the bushing. And this is part of our bushing monitoring system, MSENSE BM. And now thank you very much for your attention. And we'd like to answer some questions that came up in the chat.
Thank you very much, Laurenc and Tobias. This was really an incredible startup for today, for this morning. So we have the first questions ready. So which faults can be detected with the MSENSE BM monitoring system?
Maybe I start and then hand over to the expert, to the bushing expert. But as you could see in the first slides from Laurenc, there are failures where foils actually, where you lose foils, so where you lose capacitive layers, where the main capacitance increases. And as this is one of the major things that we monitor, we can also ensure that we can that every event that leads to a loss of these foils, that we can detect this. And this is actually probably the most critical one. And I have to ask the expert: do you need to be able to detect the loss of one layer or even more? And can MSENSE BM do that?
Yes, we have seen that MSENSE is able to detect the loss of layers, and they can have different reasons. A typical reason would be partial discharge. If you get a void in your bushing and it starts to burn, you might lose the insulation capability and later on a layer. You have to look at the technology, of course, of the bushing. If it's a OIP, you should be careful, because if you have partial discharge, that might be a more faster process if you compare to RIP. RIP is more solid, so it gives you maybe more time to replace a bushing. But if you have a sensitive system, and we have here a sensitive system, you're able to detect the loss of one layer. Another important thing, or one of the most important things for bushings, is the tangents delta value. The tangents delta value basically gives you an indication how good, how solid your insulation system is. And if you have a very high quality insulation system, then you have a very low value there. And the problem is, if the tangents delta value increases over time due to moisture or aging process of the material, you get higher losses inside the bushing, and especially with high voltage bushings above 245 kV, the impact might be severe, because if you're not able to get rid of the temperature that's generated inside the bushing might explode on the transformer, and you don't want to happen that. So it's very important to look at tangents delta values, and MSENSE BM is doing that. So you have a possibility to detect such failures before it's too late for your bushing.
Thank you very much. The next question I have: does the measuring system have to be serviced, or is a calibration necessary during the period of use?
So there are actually two questions in one. Maybe to begin with, if we start the life of a monitoring system, we need to look at, is it new bushing? Is it already applied at the transformers manufacturer side? Then we can assume that the test type protocol is sufficient enough to get the values out of this. So the typical C1 of the bushing and the typical tangent delta of the bushing to begin with. So because always when you want to do condition assessment, you need to know the history. So this is one really important step. And so this is for new transformers. And once it is configured, once it is applied, we don't need additional calibration in the field. But there is actually a second thing to talk about, which is if you apply bushing monitoring on an aged transformer, on aged bushings, and want to retrofit the system, then we would recommend to perform a diagnosis measurement beforehand, because you don't know if something has changed and you don't know the start point of the bushing. What would you say?
Yes, I
Laurenc?
agree. Very important, as I already mentioned before, that when you have older equipment, it makes sense to do a diagnosis on the bushing, and if you do so, you should know the history of the bushing.
Yeah.
And you can do a diagnosis at site, of course. So equipment is available.
Thank you very much, Tobias and Laurenc. Another question. How many bushings can be monitored with the MSENSE BM at the same time?
Yeah, this was actually one of the last slides that I was showing. Always a set of 3 bushings. So we always need to be sure that we are in a 3-phase system. So it's either 3, 6, 9, 12, probably not more than that. But this is always the one thing to take into account if you want to apply MSENSE BM. It's possible on every bushing on transformer, but it has to be a 3-phase system. Yeah.
Great, thank you. And the last question I have for now somehow connects a bit. Can the MSENSE BM also be used on a single-phase or outer transformer?
It cannot be used on a single-phase transformer, so we are not able to monitor one single phase. But of course it can be used in an auto transformer, because usually auto transformer is designed as a bank, so means 3 phases in 3 different transformer tanks, or it's one transformer tank with 3 phases, so that can be monitored, of course.
Okay, so 3 single-phase transformers in a set, in a bank together is definitely possible as well with the MSENSE BM system.
Yes, right.
Thank you very much, Tobias and Laurenc, for your time.
Thank you.
It's really a great presentation. And we will be back for you around 10 o'clock European time with our next presentation. Thank you very much. Goodbye.
Bye.
Thank you.